I'm Richard Norris, and my project partner is Ben Patterson, who will be speaking in the second half of this video. Our Part 4 project is the aerodynamics of gliding birds. So to give you a quick introduction to what our Part 4 project is, we looked at analyzing the external flow around a giant petrel and albatross wing, and that was done via wind tunnel testing and computational fluid dynamics. We also look at the processes and setups to conduct accurate wing analysis in wind tunnels and computational fluid dynamics. So the motivation behind our project is that birds glide at low Reynolds numbers, and not much research has been conducted on low Reynolds numbers aerodynamics. So by analyzing the aerodynamics of birds and finding out what makes them glide so well, bio-inspired designs for small aerial vehicles can be developed. So our project started off by 3D scanning 2 taxidermized bird wings using a Leo 3D scanner. We exported these scans as a mesh body to Autodesk Inventor Professional, where we surface modeled the wings. For the wind tunnel testing, we 3D printed half-scale models of the wings, and we measured the X and Y forces on the wings over a range of angles of attack between 0 and 20 degrees using a JR3 force balance. The wing speeds that were tested were at 5, 10, and 15 meters per second. And from there, we obtained the lift and drag coefficients. For the CFD, the picture on the right shows the CFD setup and boundary conditions that we use to undergo CFD analysis on the wing. Again, we obtained the X and Y forces over a range of angles of attacks, and we tested the wing speeds at 5, 10, and 15 meters per second again. We compared these lift and drag coefficient values against the coefficients that were acquired from the wind tunnel. And we did a mesh refinement study just to make sure that the mesh sizing did not significantly affect the values that we got. This flowchart shows the overall timeline that we used for our project. As you can see, after the CFD and wind tunnel testing, we collected and plotted the data sets, i.e. the lift and drag coefficients, and then we compared and validated them. And if any changes needed to be made, we went back to CFD analysis and wind tunnel testing. I will now pass you over to Ben Patterson, who will discuss the results.
For the results section, the results are plotted versus the angle of attack from the wind tunnel and CFD tests, and are compared to X-foil data of a common low Reynolds number foil section, the Siegel S5010. First, we have the lift coefficient. For the petrel, all 3 sets of results are similar through the middle and low angles of attack. However, the petrel seems to stall later, and stalling doesn't decrease the lift coefficient as much as what it does for the S5010 foil. For the albatross, the wind tunnel data is quite a lot larger, but the CFD and S5010 foils results are similar. Again, there is less loss of lift from stalling from the albatross wing compared to the S5010 foil. For the drag coefficient, it is clear that the wind tunnel drag coefficients are much larger for both wings than the other 2 sets of results. The CFD results are similar to the S5010 foil with the same trends for both the petrel and albatross wings, but the CFD results are consistently a little bit higher. Now for the lift to drag ratios, the results are compared to the maximum results from live bird wind tunnel experiments of similar species. Clearly, the wind tunnel results are much too low due to the drag coefficient being too high. The CFD results of both the petrel and albatross wing show similar maximums to the experimental results. The main difference in the results is the wind tunnel drag coefficient being far too large. The reasons for this is with the initial setup, there was a free space under the base of the wing, which meant the flow could travel around the bottom of the wing due to the pressure differences on either side of the wing. This would create vortices that induce drag on the wing. Also, the drag on the mounting setup would have been recorded by the force balance. Other potential reasons are misalignment in the wind tunnel of the wings. To fix these problems, we developed a new wind tunnel setup that includes a splitter plate. The splitter plate should stop the vortices being produced at the base of the wing and overall improve the accuracy of results. However, this couldn't be tested due to the COVID restrictions. For future work, we'd want to retest the bird wings in the wind tunnel with the new splitter plate setup and investigate the effects of porosity and wingtips on the aerodynamics of the wings. Thank you for listening to our presentation.